All righty, so getting ready to get I got the live stream started here. Give me just a sec and I'll be off to the races. Okay, got that rolling. Get this video there. Let's get back to here. All right, so I think we were on page 34. I'm going to start with the screen share. So let me see if I can get that. Let's see, where was it? Right here. Whoops, forgot to hit the button. Hopefully I said the page right. Oops, wrong page. Scroll up here. Yeah. All right. So this is kind of where we were at last time. Excuse me there. So let's kind of do a quick review. If you have a collision, two objects hit, stick together, we're going to call that perfectly inelastic. It's perfectly inelastic when they stick together. Energy is not conserved, but momentum is. Elastic. Think rubber bands are made out of elastic. They're bouncy, they're stretchy, they're like springs. They tend to conserve energy. Elastic is the word for a collision which conserves energy. Okay. Some examples might be two pool balls colliding. While you don't really think of it, a pool ball is so hard, it's like a super stiff spring. And so when it hits, it doesn't compress that much. And then it almost completely conserves energy when it compresses that tiny amount and re-expands. Same thing with steel. All right. Or springs or magnets, things like that. Inelastic. Notice the difference. Perfectly inelastic, they stick together. Inelastic means it's imperfectly bouncy. So most real life collisions will fall into this category, and energy is lost. However, the blocks do not form a single mass. We'll look at some examples soon. All right, then explosions. Notice explosions are essentially collisions played in reverse. So in a typical explosion, you have one object that splits into fragments. And so when that happens, you actually get a gain in energy during the explosion because you're converting chemical energy into kinetic energy. And then a very unusual type of explosion would be an elastic explosion. So imagine you have blocks that are held together by springs, and then you let the springs release, or you compress them and magnets are holding them together. When you let go of them, in this weird case, energy is conserved. So notice the only two on this page where energy is conserved, it's an elastic collision, or you could think of it like an elastic explosion. Now, when you read books, you probably aren't going to see the term elastic explosion in your textbook, but I mentioned it just so that you could kind of see, oh, yeah, the two things with elastic in it conserve energy. So this is what we want to deal with. In addition to this chart telling you the different types, I want to remind you of something. At any point today, if you get tired of listening to me because I'm not going fast enough for you, because it's too easy for you, maybe you did this in high school and somebody else didn't. Well, here is a strategy you can use, and you can work ahead and just get as many problems done as you can. And then just kind of tune in, because every once in a while I'll say, hey, listen to this in case it's important. So there's the strategy. That's at the bottom of page 32. So if you want to work ahead, page 32 and 34 will get the job done. So let's go to this case here. Let's start with, oh, you know what? I'm going to skip ahead. I want to go to this one. 9.6. Sorry, I just like this problem. It's a nice, easy one to get rolling. So I'm going to get it written up on the board. And then we can work on it together on the board. The first one, I'm going to go pretty slowly, and then we'll rapidly pick up speed. This is 9.6. Initially, notice there's a before and an after picture, a hallmark of a good energy or momentum strategy to have before and after pictures. Okay. Just getting it drawn. I'm going to use, I guess, blue for number 1. And I guess I'll use red for number 2. Afterwards, they collide and stick together, it says, right? What type of collision is this?
Perfectly inelastic.
Perfectly inelastic, absolutely. So I'm almost ready. All right. Let's take a look at my whiteboard if I can. Here we go. I don't know if you hear my kids screaming. I don't know what's going on out there. Maybe I'll just stay in here and do physics. It's probably the smartest move. All right. Okay. So in this case, we've got 1 hits 2. 2 is initially at rest, right? I've got a before and an after picture. And somebody mentioned that in part A, this is perfectly inelastic. So it's not just inelastic, it's perfectly inelastic. That's true whenever they hit and stick together. Next, if I want to do a conservation of momentum problem, I first need to ensure conservation of momentum applies to this scenario. Now, this step we're going to gloss over a lot because we're in a chapter where it's always going to be true, but I want you to remember this. First, we should think, is it reasonable to think momentum is conserved? So here's the question you want to ask yourself. Are external forces negligible? If force external is negligible, then we could say momentum initial equals momentum final. So let's take the effort this first time to actually think about it. And let me just scoot this closer for a minute. So in this case, are there any external forces, first of all?
Yes.
Okay, what is one of them?
Gravity.
Gravity. Okay. What else do we have?
Net force.
Net force?
I mean, not net force. It starts with an N. I forgot.
Oh, normal force.
Normal force.
Yeah. What is true about gravity downwards and normal force upwards in this particular case?
They cancel each other out.
They cancel each other out. So those external forces are huge, but they cancel each other out. So it's totally reasonable that they're negligible. What about friction or anything left-right? Do we have anything like that?
Friction is negligible.
Wait. So in this case, all the external forces are negligible. And if you're wondering, how could you make friction negligible? You put little wheels on these and turn them into cars and slide them, or you put them on an air track. Okay. In this case, the external force is negligible. We could do this. So I'll just make a note up here. Force net external is negligible. That allows us to do the following. Now, I'm going to go a little bit slow here just to show you where everything comes from, but I'm not, but I think it's worth following along. Because the external forces are negligible, we could say the initial momentum of the system as a vector is equal to the final momentum of the system as a vector. We say momentum is conserved. The initial is equal to final. That's what conserved means. Next, in this case, that's going to be momentum of one initial vector plus equals plus. I'll just write the two reds. Oh, shoot. I messed up the color codes. Well, I could fix that. The order of the subscripts doesn't matter. Whoops, that was supposed to be 2. I'll fix it. Sorry about that. Sorry about that. All right. So now our system is object 1 and 2. The two objects that we are talking about the collision. So in this case, now I'm going to go one level further. I'll say, again, the 2 and the 1 and the order of the subscripts, who cares about that? P2 initial in the X. P2 final in the X. P1 initial in the X. P1 final in the X. That should also be equal. Now, before I go on, I'm going to do one subtle thing here. I want to point out, this is a vector equation. This is going to be pretty important. We know that there's actually an I hat on all of these, right? We usually don't write it because I know that the I hat is immediately going to cancel out. As a result of doing this thing this way, however, I want to point out that this could be a positive or a negative number. This could be a positive or a negative number, et cetera, et cetera, et cetera. So in this case, because these came from a vector equation, every time you do a conservation of momentum problem, I want you always thinking about, do I need to do plus or minus signs? If you could get in that habit from this problem, you're good. Now, I hope you agree everything in this problem is going to the right. So everything in this particular problem is going to be positive. So we don't really need to worry about minus signs for this problem, but future problems we might. So far, so good? One of these things is 0. That's 2. 2 initial is 0, right? Because it's initially at rest. If you recall, what is the equation for momentum?
M times V.
MV. Good. That's a vector. All right. So far, so good. So now I could just go ahead and go one more level here, and maybe I'll do it like this. M1 V1 initial X. This will be, ooh, check out the final is special in this case. Well, let's do one more line here just to see it. This is M2 V2 final in the X plus M1 V1 final in the X. Obviously, we could have done this much faster, but I'm trying to show you a process. The same technique would work if we had a 2-dimensional or 3-dimensional problem. You do the same exact thing, except you'd have subscripts Y or Z. So I'm trying to show you the most general way that we'll do this for all problems. Now, in this case, something special happened. They formed one object at the end with one final speed. So we could actually group these two because these are both the same. This is V final, and this is V final. Furthermore, this particular speed right here was actually just V in the problem statement. So we can clean that up and make this V. Next. Sorry, this thing's wiggling a lot.
Sorry,
Okay.
can you say one more time how on the right side they're both V final, not V1?
Because the problem statement said they combine and move together with a single final
Oh.
velocity.
Gotcha. Okay.
This is a special case, so this part is special to this problem only. Everything up to this line is valid for every problem. Well, maybe not this. It's possible they're both moving. But is that good, Jacob?
Yeah, thanks.
All right. So now I could actually group these another way and solve for V final, I think. Isn't that what we were supposed to solve for? I think so. So when I group these, I'm just going to watch this. We get M1 plus M2. Wait, that's M1. I keep mixing up my red and my blues for some reason. This is V final. We can group those, right? And so now when I just solve this thing, I'm just going to get lazy and say V final equals M1 over M1 plus M2 times V. Whoops. Sorry. I'm sorry about that. There we go. So here I just factored out the M1 plus M2. And then here I just did some algebra, grouped it around, divide by M1, you got it. Okay. Or whoops, divide by this and you got it. Now, with every answer that's algebraic, we should probably do some checks. What's one thing we could check?
Units.
Units. Does that look good? What are the units of this part right here that I'm circling? Just that part.
Unitless.
No units, unitless. So velocity looks good. All right, let me get this written up here. So we've got it up at the top. Just summarizing this result, we found V final. This is looking good. M1 over M1 plus M2 V. We could actually check something else up here. Does this seem reasonable to you? Does this make sense? What do you notice about V final compared to V? In particular, which one's bigger? In this problem, which of these numbers is going to be bigger, V or V final?
V.
V, yeah, because think, if you plugged in numbers 1 over 3, this would be a third of that or something, or 1 over 7 or whatever it is, or 2 over 3. So does that seem reasonable? If this object hits another thing and sticks to it, is it reasonable that it slows down? Yes. And now we see this makes sense in not only from a unit standpoint, but also from kind of a physical reality. Usually things don't speed up when they smack into something. Okay. Oftentimes they'll slow down. All right. Now, obviously, I should be careful. Things don't tend to speed up when they smack into something at rest. If you take a baseball bat and hit a baseball, that's a moving object hitting a moving object. The baseball could speed up. So that's a different problem. But in this case, running into something at rest, usually you get something slows down. Seems good. All right, next. Let me get my book out. Sorry, I moved it over here. What were we doing next? Okay, percent change in kinetic energy. So now we want to get this thing. So part C is percent change in kinetic energy. Well, that is going to be kinetic final minus kinetic initial all over the initial times 100%. Okay. You could rearrange this in a bunch of ways, but check this out. Let's just go through it. I'm going to do this kind of slowly, and a lot of calculation. You're going to see a question like this a lot of times, and there's going to be a lot of steps that you could shortcut later. So I'm going to show you all the little steps and why these shortcuts work, just to hopefully save you time later. So this is going to be 1/2. The final mass is going to be and the final speed was whereas the initial energy all came from number 1. Number 1 had mass just m1. Like that. Obviously, there's the times 100%. Let's just forget about that for now. Okay, let's do that at the end. What do you notice immediately drops out?
The coefficient.
The halves.
Yeah, that halves. Okay, is anything else going to drop out? Do you think the M1 is going to cancel out or not?
If you distribute it, yeah, right?
What do you mean by distribute? Oh,
'Cause you have, yeah.
this one's an M2. So at some point, you're going to get an M2 divided by M1, right? So it might cancel out for some of the terms, but not all of them. Is that what you were saying?
Yeah, that's what I was thinking.
Okay, okay. What about the V's? Are they going to cancel out in every term?
If you
No.
separate the fractions, they could.
I'm going to go a different way. They will cancel out if we plug in this junk up here. And this is something that might not seem obvious. If you plug this in, do you see that you're going to get a V squared right there? And then it will drop out. So if we, and notice this M1 will actually cancel out with that M1. So the M1s will cancel, the V's will cancel, a lot of stuff will cancel if we have the foresight to actually plug that in. And this is something that you probably wouldn't see right away, but a lot of these problems look like this. You do a momentum problem, you solve for the final velocity. You write down the percent change in kinetic energy. You remember to plug in that the final velocity that you solve for from the momentum problem, and a bunch of stuff drops out. That's what I wanted to get at. So let's go ahead and do this now. Okay, give me a sec. I'll move the whiteboard in just a sec. Well, let's do it now. So remember, I got to square it. So I got to square that big junk here and that junk there. Notice each term has a V squared. Notice each term has an M1, but it's a little bit tricky. I don't know if you see this. This is sneaky here. This M1 will cancel that M1. This M1 will also cancel one of those. And this M1 plus M2 will cancel one of those. So look at what we get. We get this drops, this becomes the number 1, the squared drops, and this goes away. What? You could take the time to work it out. I did this all in the solutions, but our answer is going to become M1 over M1 plus M2 minus 1. Whoops, that's a little bit off screen. Is there any way to simplify this?
Common denominator.
Common denominator. Yep. And so now, notice there's an M1 plus M2 on the bottom, M1 minus blah, 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 blah. What do we get for all this junk? What's left on top?
M2.
Nope. Close.
Negative M2.
Negative M2. Do you see it, Jesse? Because it was minus this whole thing. Okay. All right. Now there's 100% in there. So now let's just go. Wait, does this make sense? Can we get a negative number for this?
Yeah, the energy changed negatively.
Yeah, exactly. We lost energy. Let's go back. Does this make sense? When this thing smashes into there, it seems totally reasonable. You should lose energy. That means your percent change should be a negative number. Not a problem. All right, let's go take a look at the solution and see if there's anything I forgot. Whoops, wrong one. So we get this negative result here. Okay, there. Okay, that's cool. Whatever. So what I did was I'm just going to kind of put the picture up here again. So we've got it all on one screen. We've got object 1 that's initially moving with speed v, hitting object 2, which is initially at rest. Okay, and then so this is number 2. This one is number 1. Afterwards, they collide and stick together and become 1 plus 2 and fly off with some speed v final. Look at this chart and see if this makes sense. Let's start with the first line. If you have equal mass objects, the velocity cuts in half, the speed cuts in half, the energy cuts in half. This is not that unreasonable. This seems reasonable. P final, or P, let's go ahead and put P initial here just so we have it. And we could do another column, P final, just to make sure to check this seems reasonable. The initial momentum for this case is just M times V, because the initial mass was M and the initial speed was V. The final momentum is 2M times 1/2 V. Everything seems hunky-dory. P initial equals P final. You could go through and do this again. Now, what if this is 3M? If it's big, 3mv would be the initial momentum, right? Well, what's the final momentum? 4 times the mass, because you have a 3m plus an m, so a total of 4m, times 3/4 v. Notice we still get the same initial. Now, it's not the same as the first case, but it's the same as the initial for this case. So momentum was conserved. And notice you only lose 25% of your energy. So when a heavy object that is moving hits a light object that is stationary, you lose almost nothing. This would be like a bus running into a mosquito. The bus is driving, the mosquito basically doesn't change the energy of the bus at all, okay? We don't lose much speed, we don't lose much energy, good. What about the opposite? In this case, the initial momentum would be mv. We started with mass m. Notice you hit a heavy object. This would be like a ping pong ball slamming into a bird, right? Or how about a ping pong ball slamming into your face, right? Your face is so big, the ping pong ball is not going to do much to it. Okay, so, or maybe throwing a piece of noodle, throw a noodle at your face, then the noodle sticks to your face. It's not going to cause you to fall over, but you are going to lose almost all the energy. Again, notice here, we still get mv. 4m times 1/4 v gives you mv. All right. What do you think? So far, so good?
Yeah, I had a question.
Yeah, do it.
What if they're like in perpendicular paths? So one object is moving, but in theory, it's moving like left to right, but it's not like going towards
Man,
the
that's a
object.
good question. Let me make sure there's no other before we go on, Alonzo. Let me check if anybody else has a question. What do you think? Okay, let's get to Alonzo's question. Man, it's almost like, this one, right? 9.11. Let's do it. Is that what you're asking about, Alonzo?
Yeah.
All right, let's do it. So this one's a little bit trickier, but the process is identical. 9.11. So notice I actually have several pictures here. So we have a truck and a car, and they're going to smash into each other. This is the truck, and this is the car. So, and then I hope you, and so now notice that this is a top view, okay? Top view. So in this case, imagine you're in a helicopter or a drone looking down at these things. Notice this last picture is a side view. For now, let's just ignore that. Just ignore this one. Okay, this is a view just before the collision. This is a view just after the collision. Here's my question for you. Do you think this angle is going to be 45 degrees, above 45 degrees, less than 45? What does your intuition say?
Less.
Okay, and why is that?
The bigger truck is gonna have the most momentum, so it's gonna continue straight.
Interesting. Okay. Turns out that's not necessarily true. That's what I would think too, if they were going the same speed. Are they going the same speed? Maybe not. Do you see where I'm going with that, Alonzo?
Yeah.
The short answer is we don't know. Now, look at this problem right here. Look at these ones. Maybe that'll give you an idea. Okay, so I'll let you do that while I check the chat. Oh, no. Okay. All right. So, based on that, which one do you think do you think it will be closer to 45? Will it be less than 45, or will it be greater than, based on those numbers? And what is your reasoning? Somebody go ahead and give it a shot. It's okay to be wrong or to try. And I just want to try and make sure you have the reasoning right. That's all. It's not obvious, is it? The truck has more mass. The car has more speed. Which thing dominates?
The car, but slightly.
Why?
I just times it.
You did the momentum, and that's what you have to check. You got it right. So the idea is you cannot tell by the mass alone. You cannot tell by the speeds alone. You have to multiply them out, just like Gonzalo said. Remember, momentum is mass times velocity. So if you want to know who's going to win in a fight, you got to do not just the mass, but also the velocity. Okay, in this fight here, to see who gets the better angle or whatever. All right, so in this case, 40 times 600 is slightly bigger than 800 times 25. We expect the angle to be slightly above 45. Good. All right, so now let's go ahead and do this problem here. I don't remember what color I used last time, but it seemed like I kept screwing up. Was 1 number one? Blue was number one, wasn't it? Whatever, it doesn't matter. So I'm saying blue is number one this time. They're going to collide and stick together and form 1 plus 2. And then we expect it's going to be slightly bigger than 45 degrees based off the numbers we saw. Okay. What type of collision is this? Elastic, inelastic, perfectly inelastic?
Perfect inelastic.
Perfectly inelastic. Got it. Okay. They collide and stick together. Now notice this side, I'm going to give it a name, V final X. This side, I'm going to give it a name, V final Y. I hope you agree that V final X is V final cosine of phi, and V final Y. I don't know if we need this. I'm just writing it down. Okay. Okay. Next, I'm going to do the same crap I just did before. P initial of the system equals P final of the system. And then this is a vector equation. So we could do it for the P final Y equals P, whoops, let's do initials on the left. But you could also say P final X equals P initial X. Alonzo, does that give you an idea of how you would handle this? Or at least a start?
Would you assume?
Let's keep going, right? Should we keep going?
Yeah.
All right. So now let's start with X. That's going to be mass 1 V1 plus 0. This one has nothing in the X. Do you agree?
Yes.
So there's no contribution for the X for number 2. Okay. So now I'm going to keep going. And over here, this would be the total mass, M1 plus M2, times, we could just call it, let's call it V final X for right now. If I know the masses, the initial speeds, I could get V final X. Over here, Alonzo, you asked, I'm going to pick on you. What do you think I should write for the initial momentum in the Y direction? What would I get for this case? Initial momentum in the Y direction.
For when they're both together?
No, initial. So this is the before picture.
It'll be 0 for 1
Yeah, which one?
for the V1,
Yes, so this one drops out. So then what are you left with?
M1 V1.
M2 V2, because the red one is 2. So this, right, do you agree with that? Does that make sense?
Yeah.
2 is the one, because we're Y direction now. All right, so then what do we get over here? That's going to be your final. That's the M12 crap. Is that helping?
Yeah.
And this would be V final Y. Again, just so you can see this better, I'm going to scoot it as close as I can and up this a little bit. Again, the idea here is in the X direction, there's no contribution from number 2, the red one. So I just get M1 V1 because all of it's there. And then in the end, I have total mass times V final in the X. Here, and so if I needed to, I could plug in V final cosine phi if I had to. Wait a minute. Do we have any minus signs in this problem? This one's going to the right. It's positive. This one's going up. It's positive. This one's going right and up. Positive, positive, positive. We don't have any minus signs. This is good. I could get this number now. I could get that number now. I got it. Cool? At the end, what could we do? We could draw a picture. This is V final X. I know it goes this much. We know V final Y is going to be slightly larger, but not much. V final should equal the square root of right? And the angle here notice I could actually plug in these equations here. And we could get that. All right. So again, we know the numbers. We know everything about this. I'm going to pause for a second and read the question and see where we're at. Oh, my ears are killing me. Long day on Zoom. Okay. So I think we've basically done parts A through E. So let's go back to the picture and take a look at it. We talked about the type of collision. We figured out the components and figured out this. We could do all of this stuff now. We talked about whether it should be closer to the vertical. We expect closer to the vertical. So hopefully those numbers turn out that way. Now look what this is. Now consider the side view. Okay. In this case, we see an object that comes to rest after sliding. What type of problem is that? What technique could we use? There's many correct answers. Whoa. Hosh. What is it? Oh man, I thought I saw a scorpion right by my feet. I'm not exaggerating. There was a scorpion in my house the other day. I just freaked out. I thought there was I'm sorry. I think it's a feather. It has been a long day. Hold on. Yeah, it's just a feather, I think. Holy cow, that scared the crap out of me. All right, sorry. What were you saying?
I think it's perfectly inelastic. I mean, not perfect. I mean, I think it's not that. It's inelastic.
I'm confused. So yeah, that was the first part. So this was comparing these top two figures. This was a perfectly inelastic collision.
Oh yeah, sorry.
So now I'm looking at this. We have one object. It's a combined object, but it's basically one object, and it's going to slide and come to rest. What type of problem should I do for this? Does that make sense?
Oh, kinematic. Or
you could do kinematics. How would you deal with kinematics? How would you get the acceleration? That could work.
FBD?
You could do an FBD. Is there a faster way? Yes, there is. What's the faster way? We've got one other tool. We've already done momentum. We've already done kinematics, or we already talked about kinematics and forces. What's the other thing?
Conservation.
Yes, E initial plus work done equals E final. You know what I'm saying? Here's the deal. When two objects collide, we're going to do a momentum problem. When you have one object sliding around, we could do forces and kinematics, or we could do energy. Energy is pretty quick, right? Because the initial energy is 1/2 m total v final squared, right? The work done is minus mu m total GD, remember MGD, and the final energy is 0 if I put my reference level right in the middle. And so the mass total drops out. You could solve for this, blah, 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 blah. Again, two objects colliding, do a before and after picture. Write down conservation momentum. Got it. One object sliding around, try energy. If that doesn't work, then do forces and kinematics. Is that cool? Now, is there any practical application of this, or is this just a bunch of nonsense? What do you think?
You could use it to determine like who's at fault, like who's speeding.
Exactly. Right? If you want to know who was at fault in an accident, you could look at the skid marks. So this is forensics. You're examining crime scene evidence. Maybe there's video footage, whatever. You could use tracker and get an so you could try to use this information and you could tell which way the cars go and you could see who was speeding and who wasn't. Maybe one of the cars is able to track their speed and has to, like maybe the truck is constantly sending GPS information. So maybe you know exactly the truck's velocity from the skid marks or the angle or whatever this thing goes. You could figure out the speed of the car and you could void an insurance claim or put someone in jail or something. I don't know. So, or tie them up in court for many years, whatever. So there's kind of the application. I know this seems crazy, but I actually used Google Earth and kinematics to fight a speeding, or I fought the police when they said I was entering an intersection illegally. And I said, look, here's the calculations. Here's this. You can actually use this stuff. And I beat the ticket, which was good because I actually wasn't doing anything wrong. I was so pissed. I'm like, really? You pulled me over? I was doing nothing wrong. And I used physics. That was like one of the few times I was able to do something useful with my physics degree. Anyway, so, all right, enough on that. Let's check in with everybody here. What do you think? Any questions right now? All right. The other time somebody dropped a bottle on my head and I had to do the insurance company didn't want to pay. So I had to make them pay up and I had to do a calculation saying there's no way I could have dodged it based on the time, blah, blah, blah. Weird applications. So yeah, I fought the cops once and fought an insurance company once. All right. All right. Let's go back to here. So we're kind of doing things in a little bit different order. Let's look at this one. Up till now, both of the problems we've been doing, they collided and stuck together. Okay, so what do you think on this one? Take a second to read it while I get my brain wrapped around it as well. I'm going to erase the board and think. All right. What type of collision is this?
Elastic.
How can you tell?
Well, because
What do you think? It's okay to, yeah.
the spring, like
Okay,
And
that there's not a spring in this problem.
they never
but
actually.
what?
I mean, they never actually touched during the collision.
Yes. So that the magnets are acting like a spring, which is elastic, which could, yeah. So this is elastic. They're going to bounce off each other without losing any energy. Very good. So this is an elastic one. Good. So quickly, somebody other than Gonzalo. What is the percent change in energy if this is an elastic collision?
0?
Yeah, it's 0. Trick question. This means energy is conserved. So if you have a perfect, this is what's different. So for this special collision, we could actually do momentum and energy at the same time. Now, this is where you got to be careful. Momentum is a vector. Energy is a scalar. So remember, every time you're doing a momentum problem, you have to remember to do the plus minus signs, or at least think about them. So now in this case, we could do all of these, but maybe let's just pick this one right here. Okay. So in this problem, the conservation momentum would be m times v in the I hat, right? That's the initial momentum. This is V1 initial. We're going to assume that is V. And then the final momentum would be m times V1 final plus M2 is 3m times V2 final, right? Now, in this case, if we keep going, oh, whoops, and these are all in the I hat, right? That would be the momentum equation. The energy equation says 1/2 mv squared equals 1/2, I've got two energies now, m v1 final squared plus 1/2 3m. People sometimes forget the 3 in that spot. 3m times V2 final squared. So I'm just doing this one particular case. And when you do that and punch in all this stuff, it turns out something weird happens. You get a negative number for V1 final. When you have a light object hit a heavier object, it bounces backwards. And so all of our math was done according to this picture where we assume V1 final is to the right. At the end, you can sometimes get a negative number. And I actually punched these numbers in. Let's go look at them. Let's go look at the solution and see. What problem was this? 3.6, what, 9.7? This, oh, go ahead. Yeah, it was this one. I want to point out this particular problem is probably one of the ugliest pieces of algebra you're going to have in this entire course. If you try to do it without being clever, it will be painful. So what I did is I showed you a trick. So 9.7 is one I would follow my derivation. And you get these weird results here. So if you try to do this, I mean, I did some tricks in here. So you better pay attention and follow the solution for this one to save yourself a lot of time. And look what you get. Sometimes you get negative velocities here, right? And then here, notice you do get the same momentum before and after. It's kind of crazy. Look at this weird one. If you use two equal mass objects, the first one stops, transfers all of its momentum to the second one. That's like hitting a pool ball dead on. If you've ever seen this, maybe you've played pool before. And if you have, maybe you've taken a shot and the pool ball is coming in and it hits some other ball on the table. And then right afterwards, the pool ball sits in that spot and the other ball goes flying off. If you hit a perfectly straight shot in one dimension, if it's got no angle on it at all, you could actually get the cue ball to stop dead in its track and the other ball goes flying off. That's what this problem is saying. You start with M1 with moving with speed V. They have exactly the same mass, just like the pool balls. And in the end, in the final state, one of them stops, the other one goes flying off. Pretty cool. What do you think? Let me show you something else here. Now, I've got so many videos and examples of these things, right? So you can see the elastic ones are the coolest. Let's see what this one looks like. So it looks like we got a 200 and a 400. So this would be a case of a mass hitting twice as much. So now, give it a second. And I'm going to hit pause for a sec. Give me just a sec. Let's do slow-mo just so I could talk about it better. So now what's going to happen is the first photo gate that I'm pointing at there is going to measure the first velocity as it comes through. So we'll know the speed of this one as it comes flying through. So give it a sec. I don't know why this is taking so long. Oh, and by the way, this is on an air track, so it's frictionless. So right now, that one comes through. Notice it goes backwards afterwards. And we see it slows down dramatically. Okay, so these are timers here. And so we're not actually looking at the speed. We're looking at the time it takes to pass through there. And so, I don't know. This is supposed to be showing you that what we were just talking about actually makes sense. When you have a light object hitting a heavy stationary, they both go flying off in different directions. In this particular case, I used rubber bands, so they would bounce off. This, if you compare this in contrast, like we could do one like this one. Similar. I should be able to tell in just a second. So this is going to be a light one hits a heavy there. All right. Oh, so this is a really heavy one. So this is an inelastic, and it turns out it's perfectly inelastic. Notice the time goes up substantially, right? So that means it's slowed down. All right, that's cool. So this seems pretty reasonable. We're seeing these different types of collisions. I don't know if this is helping or not. Let's just pause for a sec. Oh, what's up, Gonzalo?
I have a question.
Yeah.
Is it okay to assume that if you lose momentum, you lose energy?
I like the fact that you asked. So what do you think I'm going to say?
Yes.
Usually. That's not quite a yes. So here's the thing. What if you have a rock in space and there's a bunch of debris, right? And the mass of a rock could change. And so sometimes you could actually lose some speed while gaining mass. And if the gained mass happens to just offset or maybe slightly more than offset the loss of velocity, it's possible. Now, don't get me wrong. Usually when you lose speed, you lose energy. That's just almost always true. Okay. It's just there could be a case where you could be gaining mass at such a rate that your velocity is going down slowly, but your mass is going up rapidly. So, yeah. Is that cool?
Yeah, thank you. I was just curious about that.
I think it would have to happen in astronomy, like maybe a black hole moving through space, acquiring mass very rapidly and doing. But generally speaking, as you acquire mass, you should slow down, right? Because that's a collision. But yeah, I don't know. Yeah. All right. Yeah. Here's a weird thing. Imagine you are a satellite in orbit. If you're in a low Earth orbit, there's not much air up there, but there's a little bit of air resistance. The air resistance will speed you up. Again, air resistance will make you go faster because it will lower your orbit, which converts gravitational to kinetic, and it's just small. It's crazy. There are weird. That's a very strange one. So a very tiny amount of air resistance can actually speed you up by lowering your orbit. Weird. Yeah. If you could, yeah, there's exceptions to almost everything, it seems like these days. Index of refraction. There's weird materials they say have a negative index of refraction. What does that even mean? Well, let's not talk about that. Let's go back to what we need to do. All right. So let's remind me, when does your quiz start? It's not, let's see, is it 6 o'clock sharp? 6 o'clock. So we're going to take our break at 5:50. All right. So okay. So let me see if we could do a couple more examples of this. All right. Let's get back in there. Anybody have questions? Speak up at any time. All right. Just unmute and holler at me. Whoops. I don't want that. Whoops. I need this. All right. Okay. Oh, here's kind of an interesting case. Let me go back to those videos and show you a different one. Now, this is kind of a strange case, so let's maybe look at this one here. All right, so inside of so this is a ball hanging on a string, and I just took I don't know. We know the masses of it. Okay, whatever. Let's keep going. Now, inside of here, there's a ball and there's a spring inside of there. So let me describe it like this. Inside of this is a spring gun. And so there's a ball sitting here next to a compressed spring. This ball is going to come flying out of here and smash into this ball on a string, and it's going to swing upwards. Okay? So let's just watch the video and see what happens here. Okay, at some point I'm going to pull the trigger. Watch that string. Okay, so notice that ball, the other one, I think it actually went backwards. But yeah, so we have a plastic ball smashing in there. But notice the max angle is somewhere right around in here. I'm going to let it play now. Not perfect, but approximately like that. And so I could kind of see the angle here even. This looks like 10, 20, 30, about 40 degrees from the vertical. Let's take a look at this problem and see what's up with that. Okay. Let's go to the whiteboard and just analyze this one. It's just a random one for fun, okay? There's a lot you can learn from this particular problem. What we saw here is there's well, I guess initially there's a ball here, and there's a ball coming at it with some speed. I'm going to call this stage 1, okay? In stage 2, this ball is now moving. Whoops, I should be careful. Let's not use that color for this one. In stage 2, we see this ball is moving. And the other one is maybe moving backwards, I think. Okay. Then in the next one, in a third picture, we saw this one swing up to a 40-degree angle. And it kind of comes to rest. And the other ball's long gone. My question is this. Between stages 1 and 2, what type of problem should we do? Energy or momentum?
Momentum.
Yes, there's a collision. Between stages 2 and 3, what type of problem should we do?
Energy.
Energy. There's one ball swinging up to a new height. We see yet another problem where we have a momentum problem and an energy problem together. Now, I know this is going to seem a little bit crazy, but I hope you noticed in the video, I knew the masses of the balls. So let's say we know the masses of the balls and this angle. What could we figure out? You tell me.
How fast the blue ball or the ball was thrown?
Yeah, exactly. So we could, right, if we know this energy, we could work back to the initial energy, which would give us this, we could call this V2 in stage 2. We could also get the velocity of V1 in the initial, and maybe we'd have to use video data. I don't know. So we'd have to figure out this stuff, right? So, but from there, we could work back to, we could work back to the speed of 1 in stage 1. So the idea is you could use this information to figure out the initial speed of one of the balls by doing a momentum problem and an energy problem. This is called a ballistic pendulum for this reason. You fire a bullet into something else, you figure out the angle it swings up to, you use that angle to figure out the bullet speed or the muzzle speed. When I was in school, they literally brought in a rifle into class and shot it into a block of wood, and we watched the block and we did all the math. We don't do that today for obvious reasons. But yeah, it was kind of crazy back in the day. They just bring in a gun to your physics class. Very strange. All right. So, all right. The ideas are important, though. Energy initial equals energy final for one object swinging around. Do momentum for a collision. All right. That's cool. Let's maybe look at another one. And now, this particular one, what type of collision do you think this is? What's your gut tell you? Is this elastic, inelastic, or perfectly inelastic?
Are you referring to number 2?
Yeah, during this collision, right? So remember, between stages 1 and 2, there was the collision, right? So here, the ball was moving this way. Afterwards, after the collision, there's one going here. So I would say the collision happens between stages 1 and 2. So between stages 1 and 2, what type of collision is there?
Elastic explosion?
An elastic explosion is different. Elastic explosion starts with one piece and the objects separate. So that's not it.
Would it be inelastic?
It's probably inelastic. Now, we might model this as being elastic, but we don't know if that's true. So the safest thing to do is to say this is an inelastic collision. You probably lose a little bit of energy right here. Excuse me, but we don't know that. So the safe bet is to say it's inelastic. They don't stick together. It probably loses a little bit of energy. There we go. If at the end, the energy loss is less than 5%, you might be, oh man, it's approximately elastic. And then you could go back and do it as if it was elastic. So yeah, this one is actually probably quite close to elastic. This is a very hard plastic sphere bumping into a piece of metal. It probably doesn't lose that much energy, but who knows? All right. Plastic is a little bit softer than steel, so maybe it would. All right. Jesse, you said elastic explosion, right? Let me show you what that might look like. Am I screen sharing?
No.
Oh, whoops. Okay. Here we go. So in this one, I think we looked briefly at this the other day. I think I will get my arms out of the way. Well, that was kind of crappy. Let's go to the next one. Hopefully I remember to get my arms out of the way. Oh my gosh, really? Okay, that one I kept my arms in the way too. Okay, this one I think I did right. I think this might be the one that I actually got my arms out of the way. These are the stupid things that make me take forever making these videos. You're like, whoops, I forgot to move an elbow. Reshoot. Drives me crazy. So notice we got a 210 and a 420. And then what we see in this case, this is going to measure the speeds of these as they separate, not the time. So notice the units, meters per second. 38. And then, ooh, do I get out of the way? Come on, dude. Get out of the way. Come on. Oh, that's right. I have to stop this one so that it doesn't erase the time. And then I can get out of the way. There we go. So notice in this case, we see you have these two masses. This one had half the mass and it had almost twice the speed. It's not perfect. This was, again, 420. This was 210. And so, yeah, this should be, say, 20 and 40, but it's about right. Or 0.20 and 0.40. That's an elastic explosion. Do you see the difference there, Jesse?
Yeah, I do.
Starts as one object and then they split apart. Since you brought it up, let me get out of this. Let's go take a look at one. And we're right here. So it's so fun when you guys ask questions. It's like, I don't know. It's just, class is actually interesting. Because I could try. Oh, that's not one. We'll come back to that one. Here we go. This is a little bit different. There's 3 masses. So page 40, 9.15. Take a second and maybe look at this one. And then Jesse, since you were crazy enough to ask a question, I'll see if I could pick on you and, try not to be too mean here. We got this figure. We have all 3 blocks initially at rest. So somebody was holding them together and then they're going to let go and the blocks are going to separate and move away, right? The springs have negligible mass. Okay, so the springs are attached. And so this is almost exactly like what we just saw in the video, except with 3 blocks. So do you think energy is conserved? What do you think?
Yes.
Yes. The springs conserve energy, and that's why I call this an elastic explosion. Again, they probably don't say this in any textbook, but I think it makes sense because it's basically like an elastic collision, only you start from a compressed state. Do you think momentum is conserved?
I'm thinking so, yes.
Yes, any collision momentum is conserved. Good. Do you think M2 is going to move or not? And if so, I guess which way would it move? What do you think?
Is friction negligible?
Friction is negligible. We got a frictionless horizontal surface. The springs are identical. Oh, okay. Identical spring, identical compression.
I think it will move to the left a little bit.
Why?
Because
What's
the
your thought
mass
process?
for mass 3 is larger than on mass 1.
Exactly. And so a lot of people think, wait, there's the same force in each of these springs, right? And that's true. But remember, the same force on a different mass will cause different amounts of acceleration. That means 3 is not going to accelerate as much because it's heavier. That means 1 will fly away faster, and that means this mass should end up drifting, mass 2 should end up drifting ever so slightly to the left. Now notice mass 2 is huge, so it should be moving 10 times slower than anything else in the problem, probably. But that's an accurate assumption. Here's another way to think about it. Go to the absurd limit that M3 is a brick wall. If M3 is a brick wall, I don't think you'd have any trouble believing that 2 should go to the left and 1 should go to the left a lot faster. Well, now you start scaling it down. If this isn't a brick wall, but actually a mass, we know this one's going to go this way. This one's lighter, so it's going to go that way really fast. And this one's going to go just slightly to the left. Let's take a look at how this runs out. If it's elastic and energy is conserved and momentum is conserved, we can write down 2 equations. P initial equals P final. And we also know E initial equals E final. In this problem, what is the initial energy? 0 or not 0?
Not 0?
Not 0.
Okay, what should it be? Give me a number, or give me an equation.
The
Go for it, Alonzo. Try it.
potential of the spring
Yeah, what's the equation for the spring energy?
is a half mv squared.
That's kinetic, 1/2
Kx squared.
kx squared. Now that's not quite right,
Well, there's 2 springs, right?
so we double it. right? What does X mean in this problem?
When it's uncompressed, or how much it
Yeah.
compresses.
Yes, it's the amount of stretch or compression. So that's the amount of compression on that. All right. And then the final energy would be, there's none in the springs, it would be all the kinetics. Kinetic 1 plus kinetic 2 plus kinetic 3, right? So there's a way we could kind of analyze this one. Let's go in there and see what we get. What do you think, Jess? Is that good on that one?
Yeah. Just gotta practice.
Yep. And so there you go. It turns out I got a very tiny number. I got, oh, it's boring. There you go. I got negative 0.49 for that one. And so there's the summary. Great. This kind of goes through. If you weren't sure, what if you drew your picture the wrong way? So you could, it turns out you might have gotten a negative number for a speed. That just means you drew your picture wrong. So, all right. You got these solutions are detailed and you really got to kind of go through them. All right. Let me do a couple of quick fun things and then I want to stop because I think we're supposed to go on break here. I just want to mention a couple of quick things and then we'll go on break. This is a weird one. It turns out if you have a extremely overinflated basketball at home, if you can pump up the air pressure in a basketball to really high so that it's super bouncy, you could imagine this weird scenario where the basketball is moving down, hits the ground, and starts coming back up. And then you have a tennis ball. A tennis ball is not exactly a third of the mass, but it's approximately a third of the mass of a basketball. So you could imagine if you drop a tennis ball, so it's coming down and the basketball is coming up, and you dropped them almost exactly at the same time. So the basketball hits the ground and reverses direction right as the tennis ball is coming down. It's going to slam into here and go upwards. A crazy result happens. The basketball stops moving. And this thing gets going twice as fast in the opposite direction. So if you do this, you can actually cause the tennis ball to go 4 times as high because 1/2 mv squared equals mgh. The m's drop out. Notice the height is proportional to the speed squared. And so by doing this, if you take an object that's super bouncy with mass 3m, put an object of mass m right on top of it. And when I was in school, what we used to do is do this. We get 2 super bouncy balls of the right mass. We would cut a small divot in the top of one of the bouncy balls so that the other bouncy ball could literally rest right on top of it, and we'd drop it. And we'd be in a building with a 4-story stairwell. And we would sit here on the first floor or whatever, and we would drop the balls into the middle of the stairwell and then duck. And we could sometimes get it to go straight up and hit the ceiling. The problem is if you miss the angle at all, and there's a slight angle when you hit, this ball comes flying out of here so fast, it's going to hit you in the eyeball. And so what we would do is we'd drop it and then duck, and then we'd have to run out and look up and see if it went up. And if we missed, sometimes it would go like this, and it'd go boom, 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 all around all the stairwells in the building. Don't try that at home unless you do it. But I didn't tell you to do that. Okay. All right. So let's call that good. These are the weird things I used to do as a kid, I guess. I don't know. That's what I thought was the smart thing to do.